Hello, good evening.
Hi, hi. Can you hear
Uh,
me?
Yeah,
Yeah, okay. Hi,
we
Rakesh.
can.
Hi, hi. How are you?
I'm good. I'm good.
Uh,
Okay.
Long time.
Uh, should we first check if I can share the screen? Because that's very important. Right.
Yeah, you can share your file.
Right. Okay. Is it visible?
Yes,
Yes.
yes, yes.
Okay. And I can go to the full screen mode. And I hope it's in full screen mode now.
Yes.
Yes, yes.
Okay. Good.
And you can change slide and let's see whether we can.
Okay. Um, do you see any transition?
Not in. Yeah. Now we see.
Now you see,
Yes,
right?
yes, yes,
Uh,
yes.
Okay. I mean, there is some sort of this, bit of animation there.
yes.
I'm not sure in online how much it will come out, but
The animation on the front first slide, the title page, that we could
ah,
see.
the text will come one by one, kind of.
Yes.
So those things are probably
Okay.
okay. So I'm hoping the internet won't go away.
Yeah. Yeah. Here also there was a strong dust. Dust storm short while back.
Okay, okay.
So I
We
was
are having
also
rain.
sorry.
We are having rain and thunderstorms and sort of.
Oh, okay. Yeah. So I was also worried that we might lose the internet connection.
So it's like what I'll do is I'll probably sort of log in through my laptop also in case there's a power cut or something. See.
Oh, before I forget, one more thing to share that on your screen you will find that there are three dots and more is written there.
Yeah, yeah.
Yeah, so there you will find something called that you can disable the others from annotating anything on your slide.
Okay, yeah. I think that's
So
it.
please disable that.
I've
Yes.
already disabled it.
Mm.
Okay. There is no issue with the things, right? Because I've logged in from two devices now. Just in case there's a power cut. So the laptop
Okay.
will take care. Okay, good. Okay.
So when is the semester ending there?
So, I mean, we are at the last phase of exams. I think today was the last exam day.
Oh, okay.
And then we'll have makeup exam next week.
Okay.
So, effectively, the semester is finished.
Hmm.
The 3-4 days, we will submit all the grades.
Okay.
I think officially the holidays have started from tomorrow. I mean, will start from tomorrow.
Okay. Okay.
Semester and semester updates. Yeah.
Hmm. Yeah, we'll have our exam starting from next week.
Oh, your exams are starting from next week.
Yes.
That's a bit late.
Yes.
Uh-huh. No, here the weather is crazy. I mean, I think we are less than 30 degrees right now, so it's
Oh, okay.
cold now. It's a very good time to visit Kanpur.
Yeah. Yeah, which is a rarity, I think, in summer.
So how many people do you expect for these talks?
Uh, Shubhayan probably would have a better idea. I think roughly between 40 and 50.
Around 55 have registered.
Okay. Okay.
Actually, this time we were a little unsure because at some places exams might be going on.
Right.
So those students who have their exams might be a bit reluctant to join.
Right. Right. Right.
So, Rakesh,
So should
can
we
we,
start?
we can start now because
Okay.
it is now 6:30.
Yeah. Or should we wait for a couple of minutes more?
Yeah, we can wait.
Whatever you say. Whatever you say. If you think we should.
So we can wait for 1 minute and then we can start.
Okay. Okay, so maybe I can start. So, hello and welcome everyone to this eighth colloquium in the LNMIIT online colloquium series. And we are very pleased to have Professor Aditya Kelkar with us to talk about some of the work that is done in his lab. And before we begin, let me briefly introduce Dr. Kelkar. So, Dr. Kelkar earned his PhD from the Tata Institute of Fundamental Research at Bombay in the year 2009, after which he held a couple of postdoctoral positions. One was at Max Planck Institute for Nuclear Physics in Heidelberg, and the other was at the University of Innsbruck, which is in Austria. After finishing his postdocs, he came back to India and joined as a faculty in the Department of Physics at IIT Kanpur in the year 2014. And as you know, as you can see from the title, His work focuses on atomic and molecular collisions and to extract physics out of by studying these collisions. And there are various aspects to these collisions, and he'll be telling us on enlightening us about some of these aspects. On a personal note, I can say that Dr. Kelkar was 1 year senior to me at TIFR when I joined as a PhD student there. And in fact, uh, his was the only name I knew when I went to TIFR because we happened to have a common friend. So without further ado, let me invite Dr. Kelkar to deliver his colloquium on atomic collisions, understanding the fascinating world of Coulomb interactions.
Okay. Thank you, Rakesh, and thank you, Suman, for this invitation.
So let me just make one more comment.
Sure.
So, students, if you have any pressing questions during the talk, please raise your hand. Or you can, if you are shy and don't want to ask the question directly, you can type your question in the chat box. And if you think that the question can wait, then we can take up the questions at the end of the talk. Aditya, yeah.
Yeah. Okay. Yeah. So thanks, Rakesh, and thanks, Shubham, for this invitation. And as displayed on the slide, my name is Aditya Kelkar. I am from Department of Physics, Indian Institute of Technology, Kanpur. And today I'll be talking about atomic and molecular collisions, particularly sort of basing the talk on Coulomb interaction, the well-known Coulomb interaction that we all have studied previously. Okay. So I'll start my talk with sort of some general comments. So physics is a study of nature, and nature reveals itself through collisions. Collision of ideas presents new solutions. Collision of ideologies leads to a new world order. Collision of characters reveals right from wrong, and collision of personalities makes or breaks relationships. So effectively, collision is all around us. In fact, that's how the world progresses. We get information about our immediate surroundings, right? And we discover new laws. Okay. The plan of talk is as follows. It's the good, the bad, and the ugly. The good is typically why and what. So because that keeps the motivation alive, that is a driving force. And in that, I would briefly discuss in very simple terms what are collisions and the scattering basics. And then comes the nitty-gritties of any experimental area, the bad and the ugly, which is basically how do you study these things, what is needed, and how do we get the information out. Again, in this part, I would be mainly talking about the 1.7 eV 10-ton accelerator that we have at IIT Kanpur, the general atomic and molecular physics experiments that can be performed with such experimental setups. And I'll discuss briefly two experimental areas. One is about the molecular fragmentation, and another one is OJ-Mitron electron emission during collision process. And then I'll sort of briefly summarize the results. Okay. So let's start with the good so that everybody sort of feels happy and everybody tries to stay till the end of the talk. So physics, motivation, and relevance. Right. Okay. So we all know that atoms and molecules and then electrons, protons, neutrons, these are the building blocks of material, right? And just to have a scale, atoms are really, really, really tiny objects. So typically, they are 100,000 times smaller than the thickness of your hair, like a strand of a hair. And in technical terms, that's about 1 angstrom. Okay. Any talk on collision physics or or dealing with ions and molecules and particles, you would encounter an energy scale, which we normally describe in terms of electron volt. Now, what's an electron volt? It's the kinetic energy gained by one electron when it's accelerated through a potential of 1 volt, right? So that's electron volt. And typically, one works with energy ranges which go from 1 electron volt to a kilo electron volt, a mega electron volt, a giga electron volt, and the ultimate limit at the present moment is tera electron volt, right? A TeV. Now, again, what is the perspective? How do we look at these energy scales? So, for example, if you boil water, which is about 100 degrees centigrade, the energy per unit per molecule is about 1 milli electron volt. That's 10 to minus 3 electron volt. The visible light, the red, blue, green that we see in rainbows, each photon carries energy of about 1 to 3 electron volts. Medical X-rays, if ever you have gone and taken X-ray of a broken hand or a fractured limb, the energy of photons, the X-ray photons, is about 100 kilo electron volt. In fact, some of you may have seen this old cathode ray tube TVs or oscilloscopes or computer monitors. There used to be an electron gun which has energy of about 20 kilo electron volts. So this is the kind of energy scale that one deals with when we are talking of electron volt scale. Okay. Now, the next slide, I'll be discussing, showing you several phenomena, and there is a short disclaimer that it's just a representative of natural phenomena around us. Any similarity to other subject areas is purely fundamental, and nobody should take offense to that. Right? So, what is this collision? ये collision क्या है? Right? If you want to study structure of protons, one hears words like quarks and gluons. This information comes from collisions. Structure of nuclei, proton, neutron, the arrangement, again it comes from collisions. The aurora borealis, the northern lights, that fascinates everyone. The process that take place in the ionosphere, that's also because of collisions. In fact, the rainbow, light scattering, it is part of collisions. Chemical reactions are also because of colliding molecules and radicals. A famous example is, not for chemical reactions, but a well-known example of collisions is Brownian motion. You can see dust particles dancing around in a ray of light, sunlight. Entire atomic theory, entire atomic structure is because of these collisions. Right? So they are present in all different branches of physics and science at a broader extent. Then what we also hear about when we talk of collisions is these different domains. For example, one looks at experiments at high energy physics. When somebody works in nuclear physics, we call them nuclear scientists. And then people like me who work in atomic physics, or we like to call it atomic and molecular physics. The energy scales change depending on what is your domain. For example, you also hear about high energy particles, low energy particles, medium energy particles, right? And then we have lasers, high power lasers, low power lasers, extreme photon sources, right? Where nobody even talks about collisions, right? It's mostly light shining on mirrors and passing through materials. And then we have chemistry, which is not even physics, right? It's mixing of, in labs, it's mixing of liquids to make new compounds, to create new gases, new molecules and things like this. And all of this is basically collisions, right? And once we hear about all these things together, it is sort of exhausting, it's daunting that what is it that we are talking about? Is there a common thread through which one can understand all of this as one domain, right? So yes, there is a common thread, but to get to that common thread, we need to fix up some fundamentals about the collisions, right? Now, any collision, be it on the football field, be it between two people, be it at the atomic scale, molecular scale, the way we describe collisions are in terms of one is the interaction time, like for how long you interact with the other system, right? And in terms of collisions in our area in experimental science, the interaction time is governed by the speed and the distance of the interacting particles. So, for example, you can have atoms which cover a size of about angstrom, two galaxies which are at astronomical units or even larger units. Similarly, the speeds can vary from the speed of, let's say, typical Brownian motion, some few millimeters per second, to relativistic speeds. Very high energy particles would actually travel at speed of light. Right. Another important parameter to characterize the collision is the interaction strength. Right? Are you shaking hands, or are you literally in a sumo wrestling arena where you bump onto each other? And again, the interaction strength can be described as a tiny prick which sort of probes the system, disturbs it ever so lightly, that you don't sort of modify the system but get to know its response. Or it could be the famous Sunny Deol's Dhai Kilo Ka Haath, where everything simply shatters down. But do we have a fundamental or universal unit or a scale of measurement to characterize this interaction time and interaction strength? Right? So to do that, we need to again look at what is the time scale that we are worrying about. When we say fast or slow, when we say high and low, what is it? What is the phenomena that is concerning behind that? Because, for example, if you look at Usain Bolt, I mean, Usain Bolt nowadays do not run. Now we have new 100-meter runners, very fast runners. But Usain Bolt broke the sort of the 100-meter record, and he ran typically at 36 kilometers per hour. That's really, really fast from human standards. But then a cheetah can easily outpace you, and it runs at about 60 kilometers per hour, right? And then that is not even fast enough, because the advanced trains nowadays, they go at 500 kilometers per hour. And beyond that, you have aeroplanes which go at 1,000 kilometers per hour, and then space shuttles which go at 10,000 of kilometers per hour. So just the speed won't sort of control my time scale. I also need to worry about the distance over which the speeds are going to be maintained, right? So speed plus distance, that's going to give me the interaction time. And in the domain of atomic and molecular physics, this interaction time or this speed would be in comparison to the motion of electrons inside the atoms. So everything that I described in terms of fast and slow, that's compared to the motion of electrons inside the atoms. And just to sort of make you recall, typical electronic speeds inside an atom from the general Bohr model would be of the order of 10 to 6 meters per second. So my fast and slow is compared to this speed, right? Similarly, we can talk of collision strength. We can have gentle collisions, which again simply perturb the system. So we call it small perturbation. And for example, and because we are talking of Coulomb interactions, it's mainly the charge particle interaction. So let's say if you take a proton with a single unit of electronic charge, it would disturb the system slightly. So that would be characterized as gentle collisions. Whereas you can have very violent collisions. For example, if you bring up a uranium nuclei with all its electrons stripped off, that's 92 electronic units of charge. And now if you do Q1, Q2 over R at atomic scale, that's a very, very strong Coulomb perturbation, which would not disturb the system, rather it would completely change the system. Again, in technical terms, this would be the H plus, the proton collision would be a correction on the Hamiltonian, whereas uranium-92 plus would be a completely new Hamiltonian for the system. And what is my basis for this gentle or strong perturbation? It's the electron binding energy. In atoms, the energy scale is governed by electron binding energy. Again, for hydrogen atom, let's say it would be about 10 or 13 electron volts. So anything of the order of few electron volts would be a small perturbation, whereas if you go order of magnitude larger than that, then effectively you are in the strong perturbative regime. So this sets up the scales, and now once you have the scale, we can start compartmentalizing different domains, right? So I call it ye tera ghar, ye mera ghar. So I have made a rudimentary table which can sort of, to some extent, distinguish between different areas of experimental science, experimental physics. You have high energy physics, particle physics. You will see that most of the times the energy scales involved are of the order of 1 GeV, giga electron volt, to 10 TeV. Now, why this energy scale is because the de Broglie wavelength of a particle with this energy would be of the order of 10 to minus 16 meters, and that's comparable to the nuclear size. That means you can probe the nuclear structure or the constituents of nuclei, and this is the domain of high energy particle physics. If I look at the velocities at these energies, they approach relativistic limits. They are almost equal to the speed of light. Nuclear physics would be about 100 keV to 1 GeV, a de Broglie wavelength corresponding to sort of looking at the nucleus from close vicinity, 10 to minus 14 meters, and the speeds are weakly relativistic, about 10% of speed of light. Atomic and molecular physics, and its extension is material science or condensed matter physics. This fall in the domain of 10 eV to 10 MeV, because what we want to do is we want to probe the atomic structure. We do not want to see the nucleus or the constituents of nuclei, but we want to see the atom as a whole with its electron cloud intact. And that gives me a de Broglie wavelength of about an angstrom. And in these energies, most of the times, one can work in non-relativistic regime. And just to highlight, so this is the part which the talk will mainly consist of, 10 eV to 10 MeV energy range. And just to sort of close this up, chemical reaction, because somewhere I mentioned that chemistry is also part of collision. So chemical reactions, the energy scales are 10 milli electron volt, that's about room temperature, to 100 electron volt if you heat the material to 1000 degrees, 5000 degrees and all that. And the length scales are about microns. So that's your large molecular size, Rydberg atom size, and the speeds are your normal thermal speeds, few centimeters, few millimeters, few meters per second. Right? Now, why do we need collisions? Why do we need energetic particles? Why charged particles? So the answer to all this is our fundamental goal is to study structure and dynamics of these constituents, building blocks of the material around us, right? Vis-a-vis atoms. So we do require accelerator for this, for accelerating the charged particles. Now, what is an accelerator? Well, it's not an escalator, right? And that's the PJ for the talk. However, we can describe it more technically. It's a device that can accelerate a charged particle, right? Now, accelerators provide largely a unidirectional, monoenergetic beam of particles in a well-defined ionic state. Unidirectional is your propagation vector, the direction, the velocity in which the particle is moving. Monoenergetic, that means it has a particular speed and direction. And well-defined ionic state means what is the charge on the particle. It could be an electron with 1 unit of charge. It could be a proton with, again, 1 unit of charge. Or it could be ions with 1 electron removed, 2 electron removed, or so on. Effectively, in terms of the basic quantum mechanics that some of you might have encountered, the accelerator is providing us particles with a particular state, particular quantum state, right? That's a wave function, initial wave function of these particles. Now, how can one accelerate a charged particle? It's very basic, very simple, because we only have one particular way. It's electric field. Nature provides us electric fields. We can create electric fields, and that's the only way we can control energy of charged particles. In fact, by the way, that also answers why we require charged particles, because we do not have any other way of accelerating systems. These are not mechanical systems. I cannot push them. Electron is so tiny that pushing it and accelerating it is impossible. Electric field is the only way to accelerate these tiny particles. And different accelerators that you might have heard of or you will encounter if you are interested in this field. This categorization is purely based on the different ways, the different technologies which one uses to create this electric field. So in general, for example, we have broadly, one can categorize the accelerators into different domains. One is Cockcroft-Walton type accelerators. Cockcroft and Walton were two scientists who in 1932 created the first particle accelerator. It uses a DC high voltage potential device to create high voltages through which you accelerate the particles. And technologically, the limit is about few megavolts. We can have a Venn graph. This used to be part of the higher secondary syllabus a few years back. So it's a Venn graph accelerator. It came up in 1950s. Again, it's a DC accelerator, creates high voltage and then accelerates particles when they pass through this high voltage. And again, the technological limit currently is about 25 megavolts. You cannot make a DC accelerator which generates more potential than this. But for accelerating particles to higher energies beyond this 25 or few megavolts, one can use cyclotrons, which are again now cyclic accelerators, which use AC field, not the DC field like high voltage fields, but the AC high voltage fields. And then a particle makes multiple rounds in the same field to accelerate successively. And similarly, a modification of this is linear accelerators, which are again basically circular accelerators, but they work on the principle of high frequency AC fields, which fall in the domain of radio frequency. They are called RF fields, and they are created using RF cavities. And the present limit, the famous LHC, the Large Hadron Collider at CERN in Geneva, the present limit is 7 TeV. It can accelerate these particles like protons and lead ions and carbon ions and other ions to 7 tera electron volts. Right? Of course, which one you want depends on what kind of experiments you want to do, but also depends on how much sort of money you have. These things do cost a lot of financial resources. Okay. Now, should we always have the biggest accelerator that is possible? And if that is the case, then why invest or why build small accelerators like the one that we have in our lab? So some of you might have read or learned this famous doha from Rahim, that Rahiman देखी बड़ेन को लघु न दीजिए ढारी, जहां काम आवे सोई कहा करे तलवार. So depending on the length scale, energy scale, and the kind of physics you want to probe, the accelerators also come in different varieties, and the experiment that can be done with one accelerator are not necessarily possible with a higher energy or a bigger accelerator. Okay, just to give you an overview of the accelerator physics or accelerator science rather, its development and its presence in India. So we have been using accelerators at various centers across nation since 1950s, so since independence. The first accelerators were a cyclotron at Saha Institute of Nuclear Physics in Calcutta, a 1.1 MV Cockcroft-Walton accelerator at TIFR Mumbai, and not only in the specialized DAE centers, but a variable energy cyclotron at Punjab University. Right. Then in 1960s, we improved and we got a 5.5 MV Van de Graaff accelerator at Bhabha Atomic Research Center, Mumbai again. The variable energy cyclotron center at Calcutta. It's right next to SINP. And again, the universities were never lagging behind. So Banaras Hindu University had an accelerator in 1960s, which was a 400 kV accelerator. IIT Kanpur got its first accelerator in 1968. This was a 2 MV Van de Graaff accelerator, which was operational till 2006. Then in 80s and 90s, the energy scale jumped about an order of magnitude. We had two similar 14 MV tandem Pelletron accelerators at TIFR Mumbai and the Inter-University Accelerator Center at Delhi. This was previously called Nuclear Science Center at Delhi. And at the same time, a 3 MV Pelletron at Institute of Physics, Bhubaneswar. In this sort of century, we have had several new additions to this. 1.6 MV Tendetron at IGCAR Kalpakkam, which is part of a experimental nuclear reactor. 1.7 MV Tendetron at IIT Kanpur. So this was installed in 2008. The 3 MV Tendetron at Hyderabad. Again, smaller energy machines, lower energy machines like 400 kV, ECR-based ion source at TIFR and IUSE, and a 200 kV ECR-based ion source at Allahabad University. And very recently, in this decade, in 22 and 23, two new accelerators were added, one 3 MV Tenditron at Saha Institute. It's called the Frena facility. This is dedicated for astrophysical research, and a 200 kV accelerator at NICER in Bhubaneswar. Okay. Now, of course, once one throws so many things, the question is obvious that what do you want to say, right? Kehna kya chahte ho? So what I want to sort of sum up is particle accelerators are the most powerful microscopes because they can look inside atoms, molecules, nucleus, and the building blocks of nuclei. They are also the most powerful missiles because they can break atoms and molecules and nuclei and its constituent particles, right? And of course, everything in between. And particularly in terms of atomic and molecular physics, what we are trying to do is we are trying to study atomic structure, constituent particles, the energy levels, orbital shapes, electron-electron correlations, selection rules, scattering probabilities, interaction potentials, so the higher order Coulomb interaction potentials, molecular fragmentation, and weakly bonded systems. And a natural extension to this is macroscopic material, condensed matter physics. So let's come to some more technical details. Interaction of charged particles. So typical interaction of charged particles is characterized in terms of ion-atom collision. So there are basic ion-atom collision processes. They also involve electron-electron correlations. One can study many particle dynamics. So when you have several charged particles present in the vicinity of each other, they will form a mean field potential, and their behavior would be then governed by this mean field. So collective behavior arises out of this, and information on these aspects is used to test state-of-the-art theoretical models, right? Which is basically then our understanding of this Coulomb field and Coulomb interaction. Beyond this basic emphasis, it has application in various branches of science. For example, the cross-section data are needed for fusion research. It tells us the evolution of astrophysical environment, the solar radiation, solar physics. Of course, in our own domain, in our own sort of surroundings, atmospheric science takes a lot of data, lot of clues from our understanding of basic ion-atom collision. For example, the formation of radiations, breakup of molecules due to cosmic rays, due to solar radiation, and accumulation of different molecules in the atmosphere. Radiation therapy and biophysics are now coming up, where you can break tumors using these high energy particles. You can study effect of sort of hazardous radiations on the biosystems. One can modify the surface and bulk characteristics of materials. So this is being used in surface physics, in surface level modification, in creating magnetism at surface. And because these particles are very tiny and they can be focused down to small sizes, one can change the structure, modify the structure at a nano scale level. And of course, a natural extension to all of this is chemical dynamics. It's just at very low energy scales. So the ultimate aim is also to, by understanding the basic physics, to control chemical reactions at a single molecule, single radical level. Okay. Now, the basic ion-atom collision process can be thought of in terms of the basic scattering and typical processes like ionization, where you emit electrons, capture, where electrons go from one atom to an ion or another radical, the target and projectile excitations, and all of this can be accompanied via emission of radiation, photons. So that's called radiative relaxation, or energy could be transferred non-radiatively, and that would be non-radiative relaxation. What one does in terms of measuring the process is we measure the cross section, which is nothing but the likelihood or probability of a certain process to take place under given initial conditions. So the kinematics of the entire collision process can be understood in terms of this schematic. We have an ion whose quantum state is completely defined. It has a particular charge state Q plus and a fixed energy and a fixed direction. I have an atom, this B, which has its own electronic structure, which is typically stationary, not moving, non-disturbed in a ground state level. So its quantum state is also defined. After collision, the ion would change its momentum as well as its charge state. There could be exchange of electrons. The ion, the target ion, we call it recoil ion now because it gets a recoil because of the collision. This Bn plus. So this would also gain momentum because of the collision. It might lose or gain electrons. So its charge state would change, right? And the electrons, which could go into continuum, they become free in this process, or they change their parent nuclei. Right? So these are the three entities which are the main players in any collision reaction. And effectively, the entire kinematics is then governed by these two fundamental laws of energy conservation and momentum conservation. If you know the energy of the particles before the collision, and you can measure the energy and momentum of these particles after the collision, then using energy momentum conservation, we can figure out the nature or the dynamics of the process which led to the change or the loss or gain in momentum and energy. And all of this, in terms of atomic and molecular physics, is controlled by the Coulomb interaction, your 1 over R potential. So this was about the motivation and the fanciness of the sort of the ideas. And then we come down to actually doing the measurements, creating different experimental setups to study, to measure the energy of these particles, to measure the momentum of these particles, to collect electrons, to look at the angular distributions. And that brings us to the tools and techniques which then form the bad and the ugly. So what are the tools that are needed? You need sources of these ions. You need to create these high energy particles so that one can perform collisions with these. So you need sources of heavy ions, accelerators. For example, this is the famous tower of TFR Peletron. This is the synchrotron facility at Indore, the RRCAT, and this is the beamline in LHC. So you need this kind of large facilities. You also require very high vacuum scattering chambers and beamlines because these particles, ions, protons, electrons, they do not travel in air, right? For them, air is too crowded. They dissipate all their energies in moving through about few millimeters to few centimeters of dense air. So you need to evacuate all the background gas for their movement. You also require novel spectrometers to measure their energies and charge and momenta, because what we are talking about are electrons and ions, and single electrons, single ions, single photons. And these are so tiny that it's very hard to control them, and you need to create specialized spectrometers to make any measurement. You also require high efficiency position sensitive single particle detectors because you want to generate a signal corresponding to 1 electronic unit of charge or 2 electronic unit of charge. The momentum transferred by these is really, really minuscule in terms of our day-to-day experiences, right? An electron has a mass of 10 to minus 31 kgs. Even if it's moving at close to the speed of light, its momentum is really, really small, right? So the signals that one generates electronically, they are of the order of nanovolt to microvolt, right? And you need to then amplify them properly. You have to discard the noise, and then you need to convert them into digital signals such that it can be stored in our PCs. And the process that we are studying, these are extremely fast process. Typical time scales vary from 10 to minus 15 seconds, that's about a femtosecond, to 10 to minus 3 seconds, which is millisecond. And that means my experimental electronics, my data acquisition system should be able to work at very fast rates. Right? So these are the tools, and most of the effort goes in creating these tools to perform a faithful experimental measurement. So now I'll come to more focused approach toward what the work that we are doing. And this is a snapshot of the laboratory that I work in, and we try to sort of keep it running as well as perform experiments. As you can see, it's a big hall. It's about 10 meter in length, and the entire hall is mostly covered by or occupied by this Tandetron accelerator. It's a 1.7 MB machine, which is installed here at IIT Kanpur in our lab. Okay. Very briefly, it of course it contains several parts, which each has their own individual sort of importance as well as functioning. So on the right hand side, you can see some specifications of the accelerator, right? Which anyway, as I discuss more, probably it will become a bit more clear. But effectively, we have few important components in this accelerator, in any accelerator. So for example, you must have a source of ions. See, ions do not come easily in nature. Most of the times we are dealing with neutral material. So to put charge on carbon, nitrogen, hydrogen, one needs to put an effort, one needs to create a proper technique. So we always start with a source of ion. And for example, in our case, we start with a source of negative ion. Now you can take, for example, C minus. So 1 electron extra on the neutral carbon atom. And the ion source is floated at about minus 25 kilovolt, such that a negative ion would be repelled from that. So that would give us a negative ion B. Once I have the negative ion, typically again what will happen is I will not get a pristine sample to create a negative ion. Material again comes in forms of mixtures and compounds. So I'll get multiple negative ions at the same time. So what I need to do is I need to mass analyze them. And this is again, these are charged particles, energetic charged particles. You can use magnetic fields to separate them in their motion path. And that's the job of electromagnet. So we have this 90-degree sector electromagnet, which we use as a mass analyzer. So all the negative ions have typically same charge. And this is a question which I'll leave it for you. And its answer will be asked at the end of the talk, that why the negative ion charge is fixed at -1 unit. But most of the times the negative ion charge would be at -1 unit. So all the particles which are created, negatively charged particles, will have -1 unit of charge. They are accelerated through the same potential. So they have exactly same energy. The only difference is mass. So when they travel in a magnetic field, their radius of curvature depends simply on the mass. And then there's a vacuum chamber, which has a fixed radius of curvature. So tuning the magnetic field, I can select a particular ion. Once a particular ion is selected, it enters the main accelerator, which is schematically shown here. Now this accelerator has a very high voltage terminal at the center of the accelerator. So it's a beam pipe, which at the center holds about maximum 1.7 megavolts. And this potential is positive. So the negative ion sees this potential as attractive potential and accelerates towards it. By the time it comes to the terminal, it has gained energy of the order of 1.7 mega electron volt, MeV. And then as soon as it comes to the center, it passes through a high pressure nitrogen gas. We call it stripper gas, because it strips off the electrons from this negative ion via collisions. And once the electrons are stripped off, a negatively charged particle becomes a positively charged particle, right? Of course, the positively charged particle is still moving in the particular direction because it has 1.7 MeV energy. And as soon as it crosses the terminal, the same terminal becomes a repelling potential for this positively charged particle. So it gains energy further. And that's why the name is Tandetron, It's a tandem accelerator. It accelerates in the incoming channel as well as in the outgoing channel. It pulls the ion, and then because the ionic charge state is changed, it pushes the ion out. So it's a push-pull configuration, which is called the tandem acceleration, and that's why the name tandetron. Once the ion beam comes out, it has gained about twice the terminal voltage energy, so about 3 MeV ion beam. Beyond this, just like laser light or a normal light beam, you need to focus the ion beam. So for this, we use focusing lens, and we have an electrostatic quadrupole triplet, which acts exactly in the same way as your normal achromatic concave, convex concave, convex or convex concave, or concave convex concave triple element lens element works. It focuses the ion beam at your experimental stations. Now, again, what happens is the accelerators take a lot of resources and a lot of time to make operational. And the experiments which are based on the accelerators, they also take a lot of time to sort of bring into a operational configuration. So usually, if an experiment is being set, you might waste a lot of time in not doing anything because you are still preparing the experiment. So that way the accelerator is not utilized properly. And to overcome that, typical accelerator facilities would have multiple beam lines such that if an experiment is being set up in one beam line, the other beam line can be used to perform a different experiment. And this is again achieved through a switching magnet, which is similar to this electromagnet. It's an electromagnet which can simply bend the beam in different beam lines. And after this, the beam goes into a particular beam line, at the end of which one can have your experimental stations. For example, in this beam line, we have an atomic and molecular physics scattering chamber, and I'll come to details of that later in the talk, where we perform these collision experiments. We can also do Rutherford backscattering and ion beam irradiation and implantation experiments at this beam line. What we also have in this facility is a unique experimental station called the proton microbeam facility. So this facility focuses the proton beam, high energy proton beam, to a micrometer size for material modification, material structuring, micron size structuring of metals and non-metallic substrates with again micron size precision. So this is about the accelerator, and then there are a plethora of experiments that can be done. So for example, in our lab, we perform experiments based on recoil and momentum spectrometer, cylindrical mirror analyzer, electron spectrometer, and projectile charge state analyzer. Again, we are looking at the three actors of collision reaction: the recoil ion, the electrons coming out, and the projectile. Right? Of course, these experiments can give us information about molecular fragmentation, ionization and capture processes, inertial processes like OJ spectroscopy, interaction with larger biomolecules or polymer chains, and radiation damage and therapy. So let's take a short commercial break because there's a lot of knowledge at one time. And the commercial break is to again give a glimpse of the kind of activities that we can do in our laboratories. So for example, we have developed, alongside doing the experiments and looking at the fundamental physics, we have developed a 10 kilovolt bipolar power supply because you need a DC power supply which can give you 10 kilovolts plus minus polarity, and you need to know how it works. Can you make it? Because if you can make it, it's easily available for you. Right? Similarly, an offshoot of this kind of work was to develop a portable handheld X-ray device. And this was a project from Indian Council for Medical Research, ICMR. And we did it in collaboration with a startup, LNMIIT Technologies. And they have actually made a camera size X-ray source which can image which can create chest X-rays, and it's portable. It can be taken to village areas, remote areas, and it can do it at a large scale. Okay, let's come back to the talk. Come back to the atomic molecular physics experiments. So I'll mainly focus on two kind of experiments. One deals with electron spectroscopy, another with the molecular fragmentation, right? So again, to coming back to the same schematic, when atom से ion टकराए, फिर क्या हो अंजाम? बदले ion. So the projectile, which after collision would change its momentum, would change its charge state, right? And that is studied through a projectile charge state analyzer. बिखरे atom, the atom would, if it's a molecule, then it would basically fragment. If it's an atom, then it can lose out its electrons, right? They effectively go out as marbles thrown on the floor. And this can be studied through recoil and momentum spectrometer, right? Which we have developed again in the same lab in our laboratory. And the tiny electron, the electrons will always come out. Change in the electronic state is what characterizes the collision, right? And these electrons are then studied through specialized spectrometers called electron spectrometers to study what is this, in what direction they are coming out, with what energy they are coming out, because they carry signature, their energy and angular distribution carries signature of the process which led to the emission or the capture of electrons. So let's look at two of these, electron spectroscopy, and I'll again focus on one particular kind of experiments based on this called OJ-Meitner electron spectroscopy. So what we are doing is we are looking at the electrons which come out of the target, or it could be from the projectile as well. Now, what is OJ-Meitner electron spectroscopy? It's an inertial process. So for example, we can take a schematic of a general atom. So K shell having 2 electrons, L shell having 6 electrons, M shell with another 18 electrons, and so on and so forth. When an ion interacts with such an atom, it can eject out 1 electron. And while this electron goes out, the outer shell electron would make a downward transition to fill that inner shell vacancy. Now, the vacancy filling, that the release of energy when it goes from L shell to K shell, the extra energy could be radiated as a photon, that's your X-ray emission, the characteristic K X-ray, or the same energy through virtual process could be transferred to another electron. So let me show this schematic to you again. The electron will make a downward transition, simultaneously transferring the excess energy to another electron in the outer shell, which then takes it, and because the energy is more than its binding energy, it can go out into continuum. Effectively, by ejecting out 1 electron from the inner shell in the primary process, we have created a 2 electron vacancy in the system, and this is called, this non-radiative analog of X-ray emission is called OJ-Meitner electron emission. The energy of the secondary ejected electron, the OJ-Meitner electron, is fixed, governed by the energy, binding energy of the K shell electron, the K shell, the binding energy of the L shell, and the binding energy of the participating L shell, right? So it's a characteristic energy for every element. And this process is named after two scientists, Pierre Auger and Lisa Meitner. Pierre Auger both discovered it independently without knowledge of each other's work. And that's why the process is now attributed to both of them. Right? Okay. Now, the kind of spectrometer that we require, we have to build these spectrometers. And again, because we are looking at electrons which are coming out with particular energy, we can use electrostatic analyzers, capacitors, to guide these electrons towards our detector with a particular energy selection. So for example, this is again a schematic of a cylindrical analyzer. So it's in cut plane. Effectively, these are two coaxial cylinders. The inner cylinder has 2 slits so that the electrons can enter and then come out. The radial field for this plane would act as a uniform field in the from outer cylinder to inner cylinder, or vice versa. Depends on the polarity of the outer electrode. Now, in a uniform field, the electrons which enter, they would do a parabolic motion. Their range can be fixed through this potential. So for every and by changing this potential, we can scan the energy of all the electrons which are going to pass through one by one through this kind of a arrangement, right? So again, I'll run the simulation again just to sort of show you what is happening in the system. So an ion plus interacts with some atom, some target, through which electrons come out, and depending on the energy of electrons and the electrode potential, they'll be guided to my detector, from where I'll have a recording signal. So there's a sort of montage of the electron spectrometer. This is how it looks in real life. This is a CAD rendition of the electron spectrometer being mounted inside the scattering chamber. The ion beam comes along one direction. The target atoms are injected into the ion beam as gas jet from orthogonal direction, and the electron spectrometer sits in the normal direction to both ion beam as well as the target atomic or molecular beam. And then the electrons are scanned over their energy spectrum, and you get an energy spectra of these electrons. These are some parameters of this spectrometer. For example, it can scan electrons from 1 eV to 1000 eV with a resolution of 4% of energy. It has a collection efficiency of about 92%. And something interesting for sort of all of us, the electron spectrometer is controlled. The electrical control of the electron spectrometer is through an Arduino Uno based data acquisition system, and the data is recorded through a Raspberry Pi PC. So one does not require very fancy, very financially intensive electronics to perform these experiments. Off-the-shelf microcontrollers like Arduino or ESP32 and Raspberry Pi PCs could be used to perform or to conduct these kind of experiments. And of course, all the experiments are automated. So the automation is done through Python codes. Okay. And on the rightmost side, you can see representative spectrum, let's say from nitrogen. And these spectra are characteristic of the element. So nitrogen will always have this OJ peak at about 340 eV. That's a characteristic energy difference between its K shell and L shell atomic levels. Similarly, argon will have this characteristic energy of about 190 to 200 eV for its L shell and M shell energy orbitals.
So Aditya, can I ask one question?
Yes, sure.
If you go to that animation where
Yes.
you were selecting the electrons.
Right.
Beforehand, if we don't know what is the, for example, energy at which the electrons are coming out, since we are trying to have an idea of, say, some unknown species.
Right.
Then we cannot guarantee that the electrons which are ejected, or in general, because it's a quantum mechanical process.
Right.
So it's not necessary that the electrons will actually pass through the slit, right?
Yes. So exactly. So what we do is, one is I can run, because say electrostatic geometry, and I know how charged particles will move in the electric field, I can run simulation to get electron energy versus this voltage calibration, right?
Okay.
So I know that at this voltage, because the angle is also fixed, right? The target position is fixed. So the electrons can enter only at a particular angle in this field, right?
Yes.
By knowing the potential, I can figure out what is the energy that will actually pass through.
Okay.
So that's when we design the experiment. And then what we do is we recalibrate our setup by doing this OJ spectroscopy. In fact, OJ spectroscopy is a signature for electron energy. So as I mentioned that the nitrogen OJ will always come at 340 eV, right?
Yes.
So now I can recalibrate my spectrometer in terms of knowing what is the voltage required at the electrode to get this 340 eV electron passing through that.
Okay.
And because the calibration is linear, after that, I have the scaling rule. And after that, what we do, again, as you said, we do not know a priori the energy of the electrons. So what we do is we scan this voltage. This this minus V of the outer electrode is scanned going from, let's say, 0 volt to 100 volt, 200 volt, 300 volt. And for each of these voltages in step, we collect the electron spectrum. We collect the electrons.
Okay.
Right. So that's how we know what is the probability of a particular energy electron hitting the detector in a particular reaction.
Okay.
Right. So yeah. So I'll just sort of give you an example of a particular experiment that we did. So to bring out sort of the kind of physics that one can investigate and then understand from these processes. So for example, if I use an argon beam, right? So we used sort of argon target. So I'm looking at OJ emission from argon atoms using argon beams as projectiles, right? So that's sort of a symmetric system. To do this, first what I did was I used a proton beam and collided it with argon atoms. And I know that argon being, the atom with atomic number 18 has a characteristic LMM line, LMM electron emission at about 200 eV, right? About 190 eV. And experimentally, we see that spectrum. So we did this for proton at different angles and we found that, okay, fine. You get a OJ emission at 150 or 190 eV. Now I change my system. I use 600 keV argon 3+. Now proton is, as I said, it's a weak perturber. It has only one electron unit of charge. It has very, in terms of atoms, it's the lightest atom, lightest species. So it doesn't carry too much momentum also. So its collision with argon is a weak collision. Whereas if I come with argon 3+, that's 3 times the electronic charge, right? And 18 times, sorry, about 40, argon mass is 40. So 40 times the momentum. So when this collides with argon, it will disturb the system in much much more violently, as well as because both are argon, the target can go and emit an LMM electron. Simultaneously, the projectile can also undergo OJ emission and emit an electron. So when we do this experiment, we see two peaks corresponding to OJ emission. One of these peaks corresponds to target. So you can see that, and of course, because the projectile is moving and the target is stationary, if I measure the same, if I perform the same measurement at different orientations of my electron spectrometer, the angular distribution of these electrons, the target being stationary does not, its emission energy does not depend on angle. So I see a fixed peak at some energy, which corresponds to target OJ. Whereas I'll see a second peak, which keeps moving from high energy to low energy. As we go from forward angle to backward angle, the angles are measured with respect to the direction of the projectile beam. So in the forward direction, when the electron comes out from the projectile, it's moving with the projectile energy. So it has higher energy. When it comes out in the backward direction, it's moving away from the projectile direction. So it loses that projectile frame energy, right? And that's why the energies are different. So this way, we can experimentally distinguish between the target peak and the projectile peak. Okay. So that's my kinematics that we have encountered. However, so let's just go back to this again. However, compared to proton, which gives you the characteristic peak, what we also see is that the peak for target OJ is also shifted. So here it was 190 eV, whereas with argon 3+ argon collision, it comes at 160 eV. There is about 30 eV shift towards the lower energy side from the target also. And now one has to worry about or think about what is the reason for this. So what one does is, as all the physics domains, one takes solace in theoretical modeling, theoretical calculations. So we calculated transition probabilities for different electronic configurations when the collision happens. And I will not go into details of this, but one can simulate the OJ process through these transition probability calculations. And what one sees is, depending on what is the state, ionic state of the target, is it neutral? Then the OJ is at about 200 eV. If it's doubly charged, the OJ peak shifts. If it's quadruply charged, it shifts towards even lower energy. So that means the energy can change depending on the ionic state of my target. Right? And now I compare this theoretical finding with my experimental result. I see a shift of about 30 eV. And if I calculate the shift from my transition probability calculations, I see that if the target was in triply charged state after collision, then the OJ emission would shift by about this 40 eV, right? So that's how one can infer that in argon-argon collision, the OJ emission is not happening from neutral target, rather from a ionized target. And once we do that, we can also use the kinematic shift, the Newtonian kinematic shift on this system to figure out and to verify that the projectile lines would actually shift by this much amount. So we can look at the OJ peak shift as a result of target ionization, and this hints towards charge equilibration of target projectile pair when we are coming with this kind of charge systems. The peak positions can be reproduced using ab initio transition probability calculations, right? And once we have the theoretical scheme, we can predict what would happen for different target projectile systems like carbon on carbon or nitrogen on carbon, which can lead to target projectile OJ emissions, and we can test out the validity of our models on these systems. Right. Okay. So that's about the electron spectroscopy. And very quickly, let's also sort of discuss a bit about the recoil ion. So recoil ion also comes out, and we study it using the technique of time of flight measurements, and the variation of that is the recoil ion momentum spectroscopy. Right. Now, what is the time of flight technique? So again, what we are doing is we want to detect and measure the energy and momentum of these charged particles, right? And to manipulate charged particles, what all I have are electric fields. So for these ions, what one can do is one can create electric field configurations. So for example, this is a spectrometer, and you create electric fields in different regions, and then there's a field-free region, and post collision, you let the electrons and ion travel into it. So for example, let's say if the pusher is at positive potential and puller is at negative potential, and I have a collision happening, I'll create electrons and ions. The electrons will be attracted towards the positive potential, so they go and hit the detector, and the ions will go opposite to the field direction and towards the sort of negative electrode, and they will go in this direction. They will travel this path. This path is long, so they take some time to travel this path, and they'll arrive at my detector. So signal at my detector comes for different ions and different charge state. It comes at different times. The time of flight of these ions is proportional to the square root of mass of the ion and charge of the ion. So if I do this measurement on the detector, I get a time of flight spectrum, which I then convert into mass to charge ratio. And for example, if I do it with C60 carbon fullerene, I'll get these different peaks, which each correspond to a different charge state or different mass of these molecular, like sort of molecules or different radicals, different fragments. Right? So that's a general time of flight scheme. And then what we do is we modify it slightly so that we can get information about not only about the time of flight, which then corresponds to the momentum along the field direction, that is my PZ, but also the position of these ions when they hit the detector, and that gives me the information about the other two momenta components, Px and Py. If you get information about Px, Py, and Pz, you can reconstruct the kinetic energy of this kinetic energy of the ionization process, right? So together we call it momenta and kinetic energy release measurement. So this is a sort of different parts of the spectrometer. This is how the actual spectrometer looks, and it's designed and fabricated through a private firm, but designed in the lab and then again assembled and installed in the lab itself. Right? And this is then the main scattering chamber inside which the spectrometer is mounted. The ion beam from the accelerator comes. There's a gas line which sends the target gas in, and then we have this detector electronics which detects all these multiple signals. Okay. And again, to sort of give you kind of physical phenomena that one can study through it, I'll give you an example of the fragmentation dynamics of the SO2 molecule. So SO2 is a triatomic system and it's a gas. It comes in gas form, so it's easy for us to handle. And it's a molecule which is there in atmosphere. It can lead to sort of reduction in greenhouse heating. It's also very important industrial compound. It's also found in different planetary atmospheres. So it's also relevant. Study of its formation and reduction is important to understand how the atmospheric chemistry would take place in different planetary atmospheres. Right? So we can study it through ion collision. And what we did was we performed the experiment and we identified two major processes. One we call as two-body fragmentation, where effectively the triatomic system breaks up into two components. So for example, SO2, if it's doubly charged, then because the two positive charges are located at the same place, there would be a Coulomb fragmentation, and that would lead to different components. For example, it could lead to O plus and SO plus, or it could lead to S plus and O2 plus. That requires a change in the molecular geometry. Or you can create a triply charged SO2, which then breaks into O plus and SO double plus. Similarly, we can have a three-body fragmentation channel where all three fragments sort of separate out into different branches. So for example, you can have from doubly charged SO2, one can have O plus O plus. All the charge is balanced. So the S will remain neutral. In another channel, it could be O plus S plus, and then O remains neutral. Or it could be triply charged three-body fragmentation, which will give you all three charged fragments. So one can identify all these sort of different fragmentation process, and then we study their kinetic energy release and momentum distribution. Again, Dulles plot and Newton diagram are ways to plot these momenta distributions to understand the dynamics of the process. Okay? So for example, if I focus on one of these channels, two-body fragmentation, it's diatomic. I'll apply momentum conservation. The momentum of S plus has to be same as momentum of O2 plus, and they have to go in opposite directions. So that gives us momentum correlation. And then the sum momentum would give us some sort of a kinetic energy release. So one sees that the most probable kinetic energy is about 5 to 6 eV, right? And then this kinetic energy must correspond to the electronic state of the parent SO2 plus molecular ion. Right. One can also look at the three-body fragmentation. So for example, of doubly charged SO2 plus, there are two channels. So both channels could be studied. For example, if we take this O plus S channel, so now the SO2 has this kind of a geometry. It has a bent geometry. So S atom, O atom, O atom, they are bonded together. And now what you do is we look at their momenta when they fragment in this particular channel. We look at their momentum distribution, and then we plot this momentum distribution, right? So this is the momentum distribution plot. It's a 2D plot where there's a correlated momentum plot, but effectively each point, so all these colors, they are pixelated, and each pixel represents momentum of S neutral, O plus ion, and O plus ion. It's a sort of, so the momentum is, so the coordinate of each pixel is related to or corresponds to a particular momentum distribution, momentum sharing between S, O plus and O. Right? So for example, if I look at the pixel at the center of this plot, this would effectively correspond to equal momentum of S plus, O plus and O plus. Right? And then we get this kind of an exponential distribution. And now what we can do is we can see that the data is segregated into different regions. It's not completely distributed over the entire space. So that segregation means a particular process is taking place because the momentum distribution is localized. So we can try to identify different zones. For example, if I define region 1, let's select all the events which are localized in the center of this plot, which typically means equal momentum sharing. Now, why would a breakup process have equal momentum sharing, right? That would happen, and this is a purely kinematic scheme, purely based on momentum conservation. If you have concerted fragmentation, right? So for example, if all the three entities break up at the same time, then because of the geometry of the system, they will share same momentum, right? It's a three-body simultaneous breakup, right? This is sort of a scheme. The momentum sharing would follow the vector sum. We can plot the same thing in terms of Newton diagram, where we normalize one axis with respect to the S momentum, and then one O plus is on the upper half plane, another O plus is the lower half plane, and you can see a symmetric distribution which corresponds to this concerted fragmentation, right? And the centroid of these three would actually form an equilateral triangle because they have equal momentum. We can also look at the kinetic energy release, and you can see the net kinetic energy release. So this is the momentum distribution. This is the KER, the kinetic energy release. The black one is the total energy released in this process. And then the colored ones are energy carried by individual fragments. Now, the momenta carried by individual fragments are exactly same because that's my concerted fragment process, whereas the kinetic energy is different, right? Because their mass is different, so they are moving with different velocities. Okay. Similarly, now we can also look at this side lobes, region 2, and this effectively means that, so you can see that the data is lopsided, either segregated on one side of this center line or the other side of the center line. That means one of the oxygens is getting less momentum compared to the other oxygen, right? And that could happen if during fragmentation, the two SO bonds are not identical. That means there is a bond stretching. So that's a molecular geometry change. That's a vibrational state change.
I think there is some audio problem.
Yeah. Am I audible?
Yeah.
Yes, yes. Now you're.
Yeah. Okay. Yeah. Right. So Coulomb fragmentation depends on this bond length, and this asymmetry here corresponds to asymmetric bond length of the two SO bonds. And now in this region, if the initial geometry is asymmetric, but the fragmentation is concerted, then again the momentum sharing would slightly change, and you will have this kind of a side lobes. Again, in Newton diagram also, you can see the asymmetric momentum distribution, right? One O plus has larger momentum compared to the other O plus. We can again plot the momenta and kinetic energy plots. And now here it's visible, tagging on to this data, one can see that indeed the momentum of S, O plus and O plus are different, right? Similarly, of course, the same effect would show up in the kinetic energy release also. So this tells us about the geometry and vibrational state of the molecule during collision and fragmentation. Similarly, we can look at this small count, localized count at the bottom of this plot. Now, this region corresponds to momentum sharing between O plus and O plus, but zero momentum for the S neutral, right? Okay. Now, this cannot happen in the bent geometry there is no way momentum can be shared between O plus and O plus such that S does not get momentum. But this can happen if the original geometry of the molecular ion changes from bent geometry to a linear molecule like CO, right? Sorry, CO2, right? So if SO2, because of its ionization, becomes a linear molecule, now what can happen is the two SO bonds can break simultaneously. The two oxygen could move in opposite directions such that the middle S would get equal and opposite kick from both of them and would not gain any momentum, right? And that would correspond to this region. So it tells us about the linearization of the molecular ion. Similarly, now I'll sort of speed up a bit because it's more repetitive. But similarly, we can look at the other channel, O plus S plus O. We can generate the Dulles plot for this channel. We can create a Newton diagram. What we see is this Newton diagram is very different from the previous case. The Dulles plot is also very different. Here, most of the data is sort of spread out in one part of the Dulles zone, right? This also carries signature of this fragmentation process. There's a fast breakup fragmentation, concerted fragmentation channel, and there's a delayed breakup. The two SO bonds need not break simultaneously. They can break one after another, right? And that would typically lead to rotation of the secondary molecular ion, and which gives this kind of a elongated distribution, basically semicircular distribution in terms of momentum. Right? So this is sort of a scheme where you have a two-body breakup, and then the second two-body component breaks up in another two-body breakup. Right? What we can further do is we can isolate regions of this Dulles plot, right? And we can make a molecular reel. We can make a video of how the molecular geometry changes. So for example, if I start from the very far end of this Dulles plot, and I plot Newton's diagram here, I see that circular structure. This is signature of the delayed fragmentation. As I come towards the center, I have the delayed fragmentation, but I also have sort of localized features which correspond to concerted three-body breakup. I come more in between, more towards the center. The semicircular part starts to die out, and I have fixed localized structure. Come in more in, the localized part is now dominant, the semicircular part is completely gone, right? So you can see that the Dulles plot, the momentum distribution it carries signature of delayed fragmentation to concerted fragmentation over its different spatial range, right? And looking at one, we can sort of isolate a particular process. We can get the data distribution in one region compared to the overall one, and we can get the branching ratios for these different fragmentation processes. We can study the fragmentation dynamics sort of in real time in terms of the propensity or probability of different fragmentation mechanisms happening for the same collision process. So these are the kind of reactions, these are kind of collisions that one can perform in atomic and molecular physics or based on ions, and the kind of information that one can get about the atomic and molecular systems about which we normally think we know everything. We have the sort of the Bohr model and the modification on that, and we know how molecules are formed and what is the new molecular scheme and everything. But when you disturb the system, there are a lot of new processes, challenges, and surprises which come out, which need to be studied experimentally, and then a theoretical formalism has to develop for that. So with that, I would summarize. So, I mean, I'll not read out the summary, but effectively, we perform these kind of reactions. We try to investigate these processes in as much detail as possible for us. We use experimental tools. We have to develop. We take help from theoreticians also. We develop our own theoretical techniques to match and to understand the experimental data. A lot of instrumentation that needs to be done to get the experiment going, to perform the experiment. And with all this, we get some knowledge about these systems, which are in the end held by and governed by the Coulomb interaction. So with that, I would like to sort of acknowledge the group members. So Sandeep he has received his PhD degree. He will get the formal one in the convocation. Ranajit and Nitish and Sayantan are currently working in my lab. Ramkumar is a postdoc. Sahan is a research engineer, and he is instrumental in doing a lot of electronics and electrical tool development in our lab. Avijit and Rohit were the previous PhD students who basically built the entire spectrometer system and data acquisition. There are collaborators from different places with whom we interact, we share ideas as well as resources. And of course, funding is needed in all this work. So I'm definitely grateful to IIT Kanpur and DST for providing regular funding to perform these experiments. So with that, I thank you, and I'm open to any questions that you might have.
So let us thank Dr. Kelkar for a fantastic talk. Especially the students, you must have realized that how fascinating all these experiments are, where you not only get to learn the physics of the underlying system, but you also get to work in instrumentation, you deal with electronics, you have to simulate your system. So there is a wide variety of things that you get to do when you are part of a good experimental team. So now, if anyone has any questions, please either raise your hand or you type it out in the chat box.
Anupam raised his hand, and I have made him a co-host. So Anupam, you can unmute yourself and you can ask the question.
Hello, can you hear me?
Yes.
Yes, yes.
Okay, great. So Aditya, thanks for an excellent talk. And I'm actually going to ask you about sort of a throwaway remark, and I wanted a little more details on that. So I think you mentioned that you can use the proton beam to fabricate micron-sized features.
Right.
And if that is the case, there were two questions regarding that. One is, what is the minimum feature size? And the second is, what is the largest transverse dimension? So can I make like, a centimeter by centimeter tile, or what's the largest size I can make?
Right. So good. So I think you are sort of familiar with this kind of experiments. So with our system, we can go down to about 10 micron in terms of the proton beam size, right? At about 2 MeV or 2.5 MeV. And what we can do, so we have two kinds of, so that's the sort of feature size that one can make, about 10 micron size. And in terms of the scale of creating these patterns, the transfer scale, we have two kind of techniques. So one is we can scan the beam itself on the target. So we have electromagnetic scanner.
Right.
That has a range of about 100 microns. Right.
Okay.
So 10 micron size over 100 micron range.
Okay.
What we also have, so that's a fast scanner. So in the sense that you can go rastering at a very fast rate. And on top of that, what we have is that target itself is mounted on a 3D stage. Okay. And that has a throw of about a couple of centimeters.
Okay,
so
great.
A large sample, then I will not promise that one can create a uniform pattern over, let's say, a few millimeter size, but one can create few hundred micrometer size patterns in different ranges of the large samples. That is definitely doable.
Okay, so that's good. So actually now let me ask sort of a more general question about perhaps other equipment at ITK. Right. What's the minimum feature size? So I think the transverse dimensions sound promising. What is the minimum feature size at any device at ITK that I can get?
Oh, you are thinking in terms of device fabrication.
Right.
Yeah, I think we have, I mean, at least from physics department, I know that we have nanolithography setups and sort of these kind of things.
Right.
Yeah. So
now
one
with the
can definitely get
nanolithography,
nanometer size samples.
right. So, okay. So now this is the challenge, I guess. I mean, on the nanolithography, what is the largest transverse dimension? I mean, can you still get, millimeter size?
Yeah, I get it. I'm afraid I'll not be able to tell you that because I
Okay,
normally
fair
don't
enough,
work
fair
in
enough.
that area. For us,
Fair
this is
enough. No,
sort
no.
of a external user beamline. So we
Okay.
completely depend on the user for that. But if you are
Okay.
interested, I think what you can do is you can probably send me a mail with the kind of
Okay.
specification that you are looking for, and I can explore
Okay.
with our colleagues that is it possible
Okay.
or what is the timeline, what is the kind of resources they require to get this done. Yes.
Great. Thanks so much. And by the way, I mean, excellent talk, and I really appreciate everything. Thanks.
So, any other questions, students? You should use this opportunity to ask questions because this was a really very interesting and fascinating talk. Okay, I don't see anyone. So, Aditya, let me continue because I'm not familiar with the kind of thing that Anupam was asking. So, what are these like features that you are talking about? What is their application? Where do you use them?
Right. So, see, let's say one very simple thing is, for example, if you take a non-magnetic substance, right?
Okay.
I mean, so typically they are like metallic surfaces. So let's say you take copper. You can take a copper sample, which is non-magnetic, right?
Yeah.
And now if I implant a magnetic impurity into it, right?
Okay.
Then I can, first of all, I can create a global magnetization into the system. And then one can study like how the magnetic features change depending on the kind of doping that you have done, right? So an implantation is a way of doing that. You can do a controlled doping.
Okay.
So that would be with a typical ion beam. With a with this micro beam facility, what we can do is we can do it at a much more localized way, right? And then we can look at the effect at a micron size scale. Let's say where you have done the doping and a region which is not doped on the same sample, right?
Okay.
So those kind of things can be done. That's like sort of one kind of study. Another feature that one can do is one can actually create mechanical channels into samples.
Okay.
Because you are using 2 MeV proton beam or carbon beam, they carry a lot of energy. And these are focused down to sort of micrometer size, 10 micron, 12 micron, 15 micron. The intensity is very, very high.
Okay.
So when they hit the material, they will actually start etching out material from the surface.
Right.
So by scanning, you can actually create these nano channels, or when people make micron size mechanical devices like cantilevers and oscillators using these techniques.
Okay. Okay, so I have a couple of other questions if it's okay.
Yeah, sure.
Yeah, so on this current slide, I see that you had this negative ion source C minus.
Yeah.
So how do you create the ion source in the first place from the neutral ion?
Right. So effectively when I have to create ions, now there are different techniques to create ions. One technique which I think most of the students might have heard of or are familiar with is plasma, right? If I can create a discharge, I will generate ions and radicals. And some of these would be positively charged, some of these would be negatively charged. Now, depending on what is the potential through which I am extracting these, is it positive or negative? I can extract negative ions or positive ions, right?
Okay.
So plasma is one technique. The source that we have is not based on plasma. It's actually based on it's called a SNIC source. A source of negative ions using cesium sputtering, SNICS, right? And the way it works is you take your sample. For example, you want carbon beam, so you will start with graphite, right?
Okay.
And what we do is we put graphite in cesium environment. So we have cesium vapor. Cesium is it's an element which you can heat and it becomes vapor. Now one uses cesium particularly because it readily gives electron. It's in the first column of the periodic table. So it
Right.
likes to give electron to become more stable. And because it's very low in the periodic table, it will give electron to most of the other elements, which have a lesser atomic number. Right.
Okay.
So, and then what we do is we have an electron source there in the ion source itself, which basically creates the cesium positive ions, which go and hit the carbon, the graphite layer, to sputter out graphite, to sputter out carbon. And in this sputtering process, the carbon passes through the cesium vapor, takes one extra electron from the cesium,
Okay.
and becomes carbon negative. And because the entire ion source is floating at negative potential, as soon as you create a negative ion, it sort of comes out from the ion source.
Okay.
So that's the scheme in this particular ion source.
Okay. Okay. So I had one more question.
Yes.
Which is a slightly general question. So these days, like there are several studies on entanglement properties for a multi-particle system. So
Right.
with the kind of experimental setup that you have,
Yes. Yes.
is it possible to, like, for any multi-electron system or atom, to see whether the bound electrons, they have some entanglement property, and study those experimentally with your kind of setup?
Right. So, okay. So, for example, this OJ process that I have talked about, right? So the explanation that I gave is more of a classical explanation, right? Because that's how we look at the process.
Right.
But the energy transfer is actually a correlated process.
Okay.
Right. I mean, we can treat it in terms of the virtual photon and all that, but it's not a step process. It's a simultaneous sort of downward transition and emission of secondary electron. Right. So there is a correlation between these two electrons. So one is studying electron-electron correlation.
Okay.
And if I look at it in a particular system, I can also, so what I can do is I can probably create an entangled system, and I can study a similar process, an analogous process, and get information about that. Get information, basically information about the wave function overlap.
Okay.
So that can be done. In fact, there is there is a process which has been discovered in last 20 years and studied to good extent now, where the electron from one atom transfers energy to another atom, another weakly bonded atom. So not in a molecule, but in van der Waals bonded systems or hydrogen bonded systems.
Okay.
So that's called interatomic Coulombic decay. And so these kind of processes are definitely studied. Another way of looking at this sort of entanglement is in terms of what one calls as the coherence length, right? So these ion beams, when they come, these ions have a coherence length, and the molecules, they act as, they act as, because they are scattering centers, the two nuclei in a diatomic molecule would act as atomic size slits for scattering of this ion beam. And that would create an interference pattern in energy domain,
okay,
whose periodicity depends on the coherence length of your ion beam.
Okay.
So these kind of experiments can also be performed, looking at the matter wave interference in these ion molecule collisions.
Okay.
Yes.
Okay. So one last chance. Anyone have any questions? No, I don't see any hands up. Okay, so I think there are no more questions. So let us thank the speaker once again for a wonderful talk.
Thank you.
And it's already quite late, so yeah, maybe we can, it's a good time to stop now. So thanks, Aditya. Thanks.
Okay, thank you. Thanks a lot. And thanks for listening. Thank you.